Last video for this section, I just want to do some rapid fire examples where a bit of everything comes into play. Some piecewise, some absolute values, some trig, just so that you can see how all this stuff applies with more difficult functions than square roots and x squareds. So let's take a look at 18. I'm going to go ahead and do 18 in the calculator just to remind you that you can. So I have a piecewise function there. To store that piecewise function, I'm going to go ahead and call it F1. Hit my define key, and then remember piecewise notation is stored in that smiley face menu. Right above sigma there is a two-piece function, there we go. And you can type it in exactly the way you would write it by hand. So we have an x squared plus 1 for my first piece. We have an x minus 2 for my second piece. And then to get those bounds in there for the piecewise function, I have a piece where x is going to be less than or equal to, and those buttons are all stored above this equal sign here. So where x is less than or equal to -1. And then for my second bounds, I want x greater than -1. So there's my piecewise functions. It's done. Control plus page add a graph will give me a pretty picture of my piecewise function. There it is. And so without even pulling up a table, without doing anything extra at all, except zooming in way too far, there we go, we can see that this has jump discontinuity. So this limit does not exist. I also want to pop one of these piecewise functions into Desmos. So taking a look at 19 here. If you just put those two equations into Desmos normally, you'll see a parabola and a straight line, but that's not a function. To include the bounds, we need curly braces. So curly braces and then our bounds. For that first one, x is going to be less than 2, and then you close it off. For the bottom one, we're going to have x greater than or equal to. Now, there's no greater than or equal to button on your computer, so you can hit the greater than and then the equal sign separate. It will automatically convert that for you. So that's nice. And that will give us our piecewise function. So again, you can do these on your calculator. I did want to show you an example on Desmos. This is another one where you don't really need to go through all the work of the table, because you can see right there 2, 6. If we're a little bit to the right of 2, it's approaching 6. If we're a little bit to the left of 2, got to select my other one now. A little bit to the left of 2, we are also approaching 6. So we don't need to go through all the work of that. So notice 20 and 21 are the exact same function, but we're looking for limits at 2 different x values. So I'm going to go ahead and do this one in the calculator. Note that I have already stored that function in there. And here it is. So the first limit they wanted us to find was at 1, or pardon, as x approaches 3. So pulling up the table and setting it up. Note that x is not in the domain. The function itself is undefined at 3. So we can't just look at the table, unfortunately. We have to change it up a bit. So menu table, I'm going to change this to ask. All right. So what's going on as we get close to 3? Start with 2.997, 2.998, 2.999. And we can see that we're approaching about -1.16. Again, you could do an extra 2.9999 if you wanted to get even closer. And maybe you're feeling froggy and wanting to get even closer than that. -1.1666666. Okay, cool. You can also go on the other side and do 3.003, and then 3.002, and then 3.001, and see that we're approaching that same value from the right as well. So approximately 1.1667 negative. Or if you're super dorky like me, you might recognize that as -76. If not, the decimal's fine. Jumping over to 21, exact same function, but now we're looking for a different value in that table. We want to know as the limit approaches 1. So this is going to be very different. Let's scroll all the way back up and we'll just overwrite all this stuff. So taking a look at 21 here, we want to know as the function approaches 1. So let's do 0.997, 0.998, 0.999. And notice those numbers aren't approaching anything. We can get a little closer if we'd like, 0.9999. These numbers are just getting bigger and bigger and bigger. The other thing will happen, let's try that again. The same thing will happen on the other side. 1.003, 1.002, 1.001. Those numbers are also getting bigger and bigger and bigger, but in the negative direction. Negative 555, negative 833, so on and so forth. That is our infinite discontinuity. If you actually look at the graph, you can see that. Turn on my smart ink here. So you can see that this function shooting off to positive infinity there and negative infinity here. Those are going different directions. So that is a limit that does not exist. So you can see that on your graphing calculator just as well as Desmos. So number 21 there does not exist. Now look at 22 and 23 on Desmos. Know that these are different functions, but we're looking at the limit at the same, one at positive 1 and one at negative 1. Totally not the same. Duh. But we'll still look at both of these two together on Desmos, starting with number 22. So 22, I already have it programmed into Desmos there. What we are looking for is the limit as this thing approaches 1. So I've got my A values already set up. Notice at 1, the function is undefined. That's this guy right here, highlighted in green. So the function is undefined at the value 1. But if we scroll off of 1 just a little bit, we can see that we are approaching a number. So I've got 0.9, 0.99, 997, 998. And then on the other side, I've got 1.03, 1.02, see if I can get closer, 1.01, there it is. So we're getting really, really, really close to a 10th. So as a decimal, you can say we're getting really close to 0.1, or you could say 1/10 as a fraction. Taking a look at 23, I already have it in Desmos as well. Note that 23 has an interesting jump discontinuity there. It looks really weird, doesn't it? And that is what we're looking for, because now I want as A approaches negative 1. So I wanted to find, as X was approaching this point, what's happening to my Y's. Well, some of them are going this way, some of them are going this way. So unfortunately, this is a discontinuous function there, so this limit will not exist. I do want to make sure I do a couple of these on Wolfram Alpha, just to again remind you that it's a tool that's available. So taking a look at 24, even already have it typed in, limit as X approaches 3 of that function. Remember to keep your numerator and denominator in separate sets of parentheses. So again, Wolfram Alpha, really quick tool, computing. It'll double check that your syntax is correct, make sure that that's actually what you wanted. It'll give you an answer, and then it will give you a graph much like Desmos, so you can double check there as well. Hey, as X approaches 3, is this what I expect? And it is. So we get -6 for 24 there. We'll also use Wolfram Alpha for number 25. Note that now this one has some absolute values in it. So on Wolfram Alpha, you can use that vertical bar as absolute values. So again, I've already typed this in. Limit as X approaches -4. That's the X value we're getting close to. And then if you're using a grouping symbol like those absolute values, I don't need parentheses for the numerator because the absolute values already group it. But we do still need parentheses in the denominator. So be careful if you're getting into Wolfram Alpha here, making sure you type that in correctly. So the reason I wanted to do this one on Wolfram Alpha is to show you exactly what it's showing me right here. Two-sided limit does not exist. They even give you a pretty picture here where you've got your function with a jump discontinuity. So they did give us the left and the right limits. We'll talk about that in the next section. What we're looking for right here is this, the two-sided limit. The overall limit of this function does not exist. The last 6 examples are all trigonometry examples, and I'm going to shoot over to Desmos in order to look at those because Desmos gives us really good graphs for trig functions. So taking a look at the very first one here, number 26. We've already seen a very similar graph. We saw the version of this with sine of 1 over x. Note that in mine I have created a slider to go ahead and kind of set up where I want that limit to be. So here we're looking for the limit as x goes to 0. And again, this function oscillates just too much. It's very similar to the sine one. No matter how you zoom in, this thing is not going to approach a y value. So this does not exist. 27 will have a limit that exists, however. So let's go ahead and pull that one up. So here we want to find the limit as x approaches 0. And this is one of those cases where the function actually isn't even undefined there. So I mean, I can move that point a little bit to the left, a little bit to the right, and we can play that same old game. But this function is going to approach that y value, that negative pi over 4. So having a picture can really help you there. We could see where that y value is approaching. Again, that's just a nice feature of Desmos. You can touch maximum values, you can touch minimum values. You can also touch intersection points, which is why I use a vertical line when I'm looking for those limits. So you can touch that intersection point between the two, and it will show you, hey, at 0, this function equals negative pi over 4. So from the left, from the right, we can see where this guy's heading. Taking a look at 28. Here we want to know as x goes to pi over 3. This is another example where the function is actually defined there. So you could look a little bit to the left, a little bit to the right, and you'll see that those values are approaching negative 0.25 or negative a quarter. So this is another example where there's not a whole lot going on here. It's actually defined right there at that point, which is what we're expecting. This was 28. No. So let's look at another one where something interesting happens. It oscillates way too much. So again, they're asking for the limit as x approaches 0, which is the point where things break. Just as a heads up, I mean, if they had asked for the limit as x approaches negative pi, for example, that's a limit that would exist. Because once again, I mean, the function's defined there. There's no issue as x approaches negative pi. The issue here is as it approaches 0. Right there in the middle of that mess, it oscillates too much. This function can't make up its mind as x approaches 0. So that's where it doesn't exist. And jumping over to our last two. The last two we could actually take care of without looking at a graph at all, but the graph is helpful. If we want to know what tangent does as x approaches pi over 2, well, pi over 2 is an asymptote for tangent. So because pi over 2 is an asymptote, we know tangent's not defined there. And if we zoom out, we see that both on the left and the right-hand side, we get two different branches of tangent. Pull out my highlighter here. One that's heading off to positive infinity, and then in the next branch, one that's heading off to negative infinity. So as x approaches pi over 2, tangent doesn't have a limit. It does not exist. Similar to the last one, it's worth noting that if I wanted the limit as tangent approaches 0, that would just be 0. If I wanted the limit as tangent approached pi over 4, for example, that would be 1. So your old trig rules still apply here. Last but not least, we have cosecant. And if they were asking us for cosecant of 0, that would be undefined, unfortunately. But they didn't ask us for cosecant of 0. They asked us for cosecant of pi, which is, oh, boo, also doesn't exist. Blah, wrong buttons everywhere. Smarty, turn on, give me green. And so here we have shooting off to positive infinity there, but then down to negative infinity here. So once again, we have another trig function where they're asking us about the limit at the asymptote. Well, at the asymptote, that limit's not defined. Half the function goes to positive infinity, and on the right side, the other half goes to negative infinity. So we have one more that does not exist. Woo! Rapid fire examples complete.